Hi, everyone. Welcome back to Organic Chemistry on YouTube. Today, we're going to continue our conversation on conformational analysis and how there are several components that comprise ring strain. So first of all, ring strain can be broken down into three parts at least. The three most important are torsional strain, angle strain, and steric strain. In the previous episode, we covered angle strain, and today we're going to talk in general terms about how these three fit together. All right, so let's talk first about torsional strain. You might recall from the acyclic structures that torsional strain happens when there's eclipsing interactions between sigma bonds. Here's an example. Remember, it's Newman projection when it looks like this is eclipsed. If that's not clear, be sure to watch the episode on Newman projections. Okay, so in an acyclic compound, you have this kind of perfect eclipsing that can happen between these two sigma bonds, which I'm highlighting in red here. Okay, those are exactly aligned with each other, and that's a torsional repulsion or a torsional strain. This can happen even more so in cyclic molecules, but it's exaggerated because the molecules can't rotate out of that unfavorable conformation. So the worst of these is cyclopropane. Okay, so here's the structure. Definitely encourage you to draw out to create these structures with molecular models. Okay, and you can see from this structure that the carbon-hydrogen bonds, which I'm going to now highlight in green, hopefully you can see it with the bolding if you can't see green, these hydrogens are exactly eclipsed with each other, both on the top and the bottom. So this is an example of torsional strain in a cyclic molecule. And don't forget, you also have a second pair of carbon-hydrogen bonds back here. So you actually have eclipsing interactions between this carbon-hydrogen bond, this carbon-hydrogen bond, and this carbon-hydrogen bond, and the same thing on the bottom face of the ring. Angle strain, so you might remember that cyclobutane, right, has bond angles that are 90 degrees or nearly 90 degrees, and the ideal sp3 bond angle is 109.5 degrees. So this deviation, right, in fact, the smaller bond angle means that these carbon-carbon bonds that flank either all of the sp3 carbons are actually closer together than they would be if they were in a perfect tetrahedron. So this contributes angle strain. I'll also label up here that this is torsional strain. Steric strain is when you have components of a molecule that get close to one another. As I've shown here with these two red lines, this indicates a steric clash. And this is a generally repulsive interaction from these groups being too close to one another, as is the case here in eclipsed propane. Okay, so now I'll go through two examples. I'll show a pair of compounds each, and we should go through and determine which one has which kinds of strain. Okay, so here I've drawn two molecules, molecule A and molecule B. Both of them are derivatives of cyclobutane. And I've drawn to the right a shorthanded scorecard, if you like, for the two compounds and the different types of strain that contribute. S stands for steric, T for torsional, and A for angle. Okay, and we're going to use this to decide which of the two molecules has a higher strain energy. The first component of this that we can look at is the sterics. Okay, so this is the closeness of these two methyl groups, right? Those methyl groups being close to one another is going to increase the steric strain of the compound. Those two methyl groups occupy the wedge positions of the cyclobutane and thus are as close as possible to one another. So I'm going to put a plus on molecule B because this molecule has higher strain energy, and a minus next to A because it has less steric strain. For the torsional strain, both of these molecules have exactly the same torsional strain. So I'm going to put zeros there because it has exactly the same number of eclipsing or nearly eclipsing interactions. And then angle strain is identical also because both of these have bond angles that both deviate from the ideal sp3 hybridized bond angle because both of these bond angles are 90 degrees in A and B. You can see here that everything's the same except for steric strain, which is higher in B. So B has more strain energy. Okay, let's do another one. We have two more cyclobutanes, but now the methyl groups are separated by one carbon. So these are 1,3 dimethyl cyclobutanes. If we look at the steric strain first, we're going to look for clashes between the substituent groups. Now, here, those methyl groups are a lot further from one another. It might not seem like a lot, just one methyl group, but actually, if you make models, you'll see that those methyl groups get pretty far from one another. So the steric strain for both A and B is almost the same. Okay, so instead of giving out a full positive, maybe we give it a positive 1/2 for A. These not only are further from each other, but have the same trans relationship that you saw in the previous example, molecule A. So this has minus in the same way. Torsional strain is identical. You have just as many eclipsing interactions in A and B, just like you did in the previous example, so 0 and 0. The angle strain is also 90 degrees. The angle strain is also the same because the bond angles are 90 degrees, which deviate equally from the 109.5 ideal angle. Okay, so that's been organic chemistry in 5 minutes or less. Thanks for tuning in.